All right, so now that we've covered all of the basics of experimental design, getting a study started, the one-way CRD model, we're ready to start talking about more specific experimental design models. And we're going to start with the most basic and most prevalent, which is the factorial treatment structure. Now, factorial treatment structure just refers to the fact that when we have a factor, remember that's just a treatment within our experiment. We can have multiple factors in a study, and a factorial treatment design or a factorial treatment structure allows us to systematically go through and look at all the complexities involved when you have multiple factors in an experiment. So Gary gives an example. He talks about when his children used to take apple slices in their lunches, and he was a really good dad, it sounds like, because he used to be concerned about whether or not the apple slices were brown. And so he went through various suggestions about keeping the slices cold and or lowering the surface pH of those apples. He could have tested browning with 4 different treatments, such as room temperature with no lemon juice, room temperature with lemon juice rinse, a cool temperature with no lemon, or a cool with lemon juice rinse. Then, in this case, he'd have 4 treatments. But these treatments, if you notice, are actually formed by combining 2 overall factors, which is the temperature, room temperature or cool environment, and lemon juice rinse or none. So a factorial's treatment structure is simply one of these, one where we have treatments that are combined by a combination, that are created by a combination of factors. This could be various things that he lists here. I think we can all think of examples of this, but in each case, the treatments are just combinations of factor levels. So when we refer to factors from now on, we're going to refer to them as factor A, B, C, or maybe by their name. But that A, B, C notation has utility to it in that we can say factor A, capital A, has little a levels. Factor B, capital B, has little b levels, and so on. With 2 factors, G, which used to refer to our generic number of levels of our single treatment, is now A times B. So think about his lemon juice temperature example. We had 2 levels. So 2 times 2 gives you 4, which was the resulting number of combination of factors that gave us our treatments. If we had 4 factors, it would just expand, A, B, C, D, and so forth. It's still making use of a completely randomized design. That's why we make sure, or I make sure, that you understand that first, because if you understand that, you can do this. You can always ignore the factorial nature when you analyze, but there's an argument that you shouldn't do that. And I think you'll understand that once we get through this chapter. So let's consider with our most basic factorial design, a 2-factor design. Here, notice that each observation, y, is indexed by I, which spans the first factor levels, 1 up to A, j, which spans the second factor levels, 1 up to B, and k, which is our number of replications within each treatment combination. Note that he's very general here, or not general, it's the opposite, not general, and he wrote N instead of Nij, so we're going to start with balanced designs, where every treatment has the same number of replications. Certain procedures, certain multiplicity procedures, in fact, are easier when you have balanced data, but a common misconception is that you must have balanced data, and I've run many an experiment without balanced data, and it's not the end of the world. So let's consider a 2-factor design here. We're going to have A equal 4, so the first factor has 4 levels, the second factor has 3 levels, so that gives us a combination G equals A times B, or 12. You can visualize all these treatment combinations using this table. So it's A equal 1, B equal 1, A equal 1, B equal 2, A equal 2, B equal 2, and so forth. So we could do an ANOVA CRD using these 12 treatment levels, We could do our pairwise comparisons. We could do everything just like we've done so far. And it wouldn't be wrong. It may just not be the best way to do it. What's nice about a factorial treatment structure is that it lets us think about the results in a different way. For example, if we ignore B, we could do the ANOVA on just the 4 groups that come from A. Then we'd have 3 degrees of freedom, and sum of squares A could denote that main effect sum of squares. I say main effect because it's for a single factor, A. Conversely, we could look at that for B. We could look at the main effect, single factor for B, and ignore A. Okay, so if we do one or the other, it's just looking at the variation between the levels of A that's consistent or constant across all levels of B. So then we could denote each of those row means by the grand mean plus the effect for A. Alpha goes with A, of course, and with our CRD assumptions from past chapters. Of course, we could use the other. We wouldn't have to assume that the effects sum to 0, just like we talked about in chapter 3, I think, but this is a predominant one. So if we did it this way, we'd be calling this the main effect of level I for factor A. We could also look at contrasts across the G groups, and we would organize them in this fashion. So notice those coefficients, W11 up to W41, are all going to add to 0 just like they did before, but they pertain to particular levels of A and particular levels of B. So since all the coefficients do add to 0, we kind of require that for it to be a contrast and not a comparison. But they could be constant across a particular main effect. So for example, we could choose 3 orthogonal contrasts. Think about 3, negative 3, 1, 1, 1, 0, negative 2, 1, 1, and 0, 0, negative 1, negative 1, 1. Then the sum of squares for this contrast would add up to the sum of squares for factor A. Okay, let's make sure we understand that. What we'd be doing is compare the first level of B. Remember here, I should have reminded you of this at the beginning. A has 4 levels here, okay? So it's going to be comparing the first level of A to the mean of the others, 2, 3, 4. Then the second level of A to the mean of the third and fourth. Then the third level of A to the fourth. Okay? Notice if you think about it, that's all the differences that could exist across the levels for A. So we have effectively made comparisons across all levels of A that should total that sum of squares because we have orthogonality. Remember, when we have orthogonal linear contrast, then we are partitioning up the sum of squares for that effect into disjoint sets. So if we do the same thing for B, hence ignoring the levels of A, we could have 3 groups determined by B with 2 degrees of freedom between them, and those would sum to the sum of squares for B, provided they're orthogonal. This gives us a sense of the variation between the levels of B that's constant across A. So ways that the responses vary across B, that doesn't matter what level of A you're at. So this is a very simple way to look at it. But again, just like before, this would say that each level of B could be modeled by mu plus beta for B, and the effects all sum to 0. And we would call this the main effect for B. So again, we could do contrasts across across B to find out something about the effect of B across all levels of A and whether or not those are constant. So for example, 2 orthogonal contrasts right here are given. This would compare the first level of A to the third, the second to the mean of the first and third. And these, because they are orthogonal, will sum to the sum of squares for B. Okay, and if we just think of this factorial design as having 12 groups, remember that's 3 times 12, our levels of A times our levels of B. We just have 11 degrees of freedom among the 12 groups. But we know we have 3 levels for A, or 3 degrees of freedom for A, I should say, and 2 degrees of freedom for B. So looking at the contrasts showing that show that they're orthogonal, we can actually be partitioning that independent variation in this sense. But if you notice, you add up 3 plus 2, that doesn't equal 11. It equals 5. Even the most math disinclined would know that. So we're off by 6, right? So there's something else going on here. There's something else when we have 2 factors, and we call this something else interaction variation. And it can only be understood and analyzed if we allow both levels of A and B to vary simultaneously. An interaction describes how the effect of changing one level of a factor, such as A, can change according to the level of the other factor, such as B. So when I talk about interaction in this class, I'll say, how does the effect of, say, A change at varying levels of B? Okay, so we could see an effect, for example, maybe lemon juice is very effective at cold temperatures, but not so much at warm temperatures. So the effect of lemon juice depends on the temperature in some way, or varies with temperature. When we break it down this way, we can think about those degrees of freedom, which remember sum to 11 for our applied example, as having A minus 1 degrees of freedom for A, B minus 1 for B, and A minus 1 times B minus 1 for the interaction. And here it's broken down in this table in that paradigm. So we've got the levels for A, the levels for B, and the interaction levels. And then our interaction constants need to satisfy more requirements. They don't just sum to 0 anymore. They need to sum to 0 across the levels for A, as in here, across the levels for B. And both must hold. And then that leaves us with A minus 1 times B minus 1 contrast. That would be 6 in our example, because remember A minus 1 would be 3, B minus 1 would be 2. So we'd get 3 times 2 gives you 6. And in a set of orthogonal contrast coefficients that compare those interaction effects, we could partition that up. So the main effect contrasts, the B main effect contrasts, and the AB interaction contrasts are all, we want them to all be orthogonal to each other in order to get this nice, neat relationship between the orthogonal contrasts and the sum of square measures. So, in recap, factorial analysis with main effects and interactions is a good way to analyze factorial designs. It's not a necessity, but it provides us deeper insight and particularly informs us about these so-called interactions. And a model that only has additive effects but no interaction is what we call an additive model, for obvious reasons. I hardly ever see additive models in practice. Almost always I see some form or some need to include interaction. We'll talk about that later.